Let's look at the global scale performance of the models first. Okay, again, and there's three charts here. There's land surface temperatures, there's combined land and ocean surface temperatures, and then rather than ocean temperatures, again, they've replaced this with ocean heat content. Okay, for whatever reason, they seem to have a better handle on the amount of heat in the ocean, but the data doesn't go back to the early part of the 20th century. Okay, same as before, blue is natural forcings only, pink is with all the human-based stuff. Okay, land surface temperatures. Okay, the models reproduce the data very, very well, and in fact, the models completely surround that black line of observed surface temperature data. They've expressed some uncertainty in that global land surface temperature back here days, but so they've dotted that line at this point, maybe removed some of their confidence in the temperature data. But the one thing that, we're not seeing that little blip stick out of there anymore. It's within the simulations, and for the early 20th century data, actually within human and natural. So maybe that doesn't completely rule out that solar explanation from before. They are predicting a little bit of human warming back then in the early part of the 20th century, but we're within the simulation. And we're within the simulation when we combine land and ocean surface temperatures. The big problem with that data was with the oceans, and it's excluded from this report. Maybe they're trying to pull the wool over our eyes. I doubt that's the case. I just think maybe that they've admitted that their data must not be so good. So let's keep our eyes on that for next time. But again, we see that on a global scale, the models reproduce the temperature data, but they only reproduce the temperature data when they include the human part of the problem. So that's pretty strong evidence in my opinion, and it's mechanistic. Still switching slides slowly here. Here's what this is on a continent by continent scale. Okay, so now in the AR4 they had this continent by continent, and on the continental scale they're not always within the simulation. I mean, in America here, that observation, these sort of Dust Bowl years maybe are creeping up to the top end of the simulation anyway. Europe and Asia we seem to have a handle on. Africa we seem to have a handle on, although that observed temperature data is off. Australia. So it's ironic here that maybe the poorest agreement in the temperature record seems to be North America. But they're sort of, it's not right down the middle anymore, except for this recent part here. And that's one of the things I noticed, that for the last 50 years, this observed temperature trend runs right down the middle of the pink simulation, with a possible exception of South America and Australia. They've also now separated this out ocean by ocean. Here's ocean heat content, and again, this is only 50 years of data, but they're simulating the ocean heat content very well. Seems to maybe something be going on weird in the Southern Ocean. Seem to have the Antarctic figured out, but here human and natural are sort of overlapped anyway. And then, Arctic, the simulation is actually sea ice. And we're simulating a human effect on Arctic sea ice, and that's creeping out below the natural part. Again, the natural simulations, and there's a pretty wide range here. Say that sea ice content in the Arctic would be level, and in spite of that being a wide range, the anthropogenic predictions now have, and that black line goes out of the natural range, if you will, and the pink range of simulations is saying something's going on in the Arctic. So there's a real discernible human impact on Arctic sea ice according to the models. Okay, and again, what are those human factors? They are mainly the greenhouse gases, together with some of these details, and some cooling due to aerosols. So really, I mean, again, this chart is built both with observations saying, here's what's happened to CO2 levels, but to get a really good idea of how those things have affected the climate, you need to run and see how the CO2 or whatever the greenhouse gases affect these models, because clearly they're getting some of this chemistry into the models now. And so there are some secondary effects that you really need to play this out in a computer simulation. So I think this is remarkably good work. And again, just to restate the key points, the greenhouse gases are by far the dominant factor, and they're us. And no existing model can reproduce the existing global temperature trends or continental temperature trends or Arctic sea ice trends or a lot of other things at this point with using strictly natural factors, with a possible exception of a few of those continental scale things. So we put the human factors in and we know what's going on. We take the stuff we did out and we don't predict the large changes. I think that's pretty significant evidence, people. At least in terms of, we better acknowledge that something real is happening here and should do something about it. So that's how we know C equals T. Bottom line, human influence has been detected in warming of the atmosphere and the ocean, changes in the global water cycle, reductions in snow and ice, global mean sea level rise, and in changes of some climate extremes. This evidence for human influence has grown since the AR4, and it is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. Okay, extremely likely. Okay, that's not here. Extremely likely means 95 to 100% probability. So the scientific community is better than 95% sure that humans have caused warming the last 20 years. And that is the mainstream consensus scientific opinion. So that's what you got. What's going on for the future? Well, that depends on what we do again. And they have made some changes. I really liked those scenarios in the AR4 because they were really rooted in human development. But there's a lot of guesswork. Simulations are not based, climate simulations are not based on human development. They're based on how much warming stuff you put in the atmosphere. So now they've gone to these things called representative concentration profiles, which essentially means you give the modelers an amount of radiative forcing, an amount of warming, and they're going to tell you what's going to happen. And then there's some variabilities in how we reach that. Okay, the most extreme scenario here is RCP 8.5, which means that we have caused a warming by 2100 or a forcing of a positive 8.5 watts per meter squared. That's the upper range scenario. And the lower range scenario is one that's called RCP 2.6, which means there's a total warming of a total radiative forcing of 2.6 watts per meter squared. And actually that goes up to about 3 by the mid-century and then back down. So that's a scenario where we rein this in pretty quick and actually turn it around. And the other ones are sort of where we level it out by 2100. Irrespective of those details, the temperature change is different depending on what kind of differences that what kind of choices we make. And one of the things that I think that gets disappointing for me when I teach this is that people get really depressed and say, well, there's nothing really I can do. This graph says, actually, there's a lot you can do. We can keep doing what we're doing and we can roast the planet and see 4 degrees Celsius of warming, which is the other direction from the last ice age. Or, we can make some sacrifices, work in the global community and change our energy infrastructure and cut back on our lifestyles a little bit and level this thing off and save the planet from who knows what. And I say who knows what because, there's a lot of uncertainty in terms of what this might mean. I don't think that's good news. I think we're going to see some significant changes, especially when we look at what this means in terms of CO2 concentrations relative to where we are now. What does that mean in terms of, let's look at these representative concentration pathways. Again, this is a little chart. I ask you about some of this in the homework. So 2.6% again goes up to 3 at some point and then declines. That means 490 parts per million of CO2, which essentially means we can still put another 100 ppm out there. And we'll get 1.5 degrees of global warming and so on and so forth. 4.5, that's 650 ppm of equivalent of CO2, and we get 2.4 degrees warming. 6, 3 degrees warming. That's so 6 watts per meter squared means an equivalent of 850 parts per million CO2, and that 8.5 means 1,370 parts per million of CO2. That means 4 or 5 times how much CO2 there was before the Industrial Revolution, and this is still rising at that point. Okay, so what do you do to get to these things? So there's lots of different inputs. Okay, so again, this is what the CO2 concentration is. These numbers were in that chart. This is what the methane concentration might look like, and what the N2O concentration might look like. Here's what this looked like in terms of global population. and so on and so forth. So all these have population leveling out. Leveling out global population sooner results in less warming, all right, 2.6, 4.5. These GDP numbers are kind of interesting. You would think that the GDP for the 8.5 scenario would be on top, and they're actually inverted out here. The highest gross domestic product is actually for the lowest amount of warming. Okay, and I haven't looked into the details of the economics there, but that's interesting. One would think that we would just run the economy like crazy and we would get the most warming, but at some point here the warming starts to negatively affect the economy, and that must be in these models somewhere. Here's what our energy use looks like. Okay, not surprisingly, if we have lots of energy consumption and lots of that is oil, notice that they predicted a decrease in oil consumption anyway around 2080 as we run out of global reserves. But you get a lot of warming with a lot of energy use, and less warming without a lot of energy use. And notice that in RCP 2.6, we start weaning ourselves out of oil a lot earlier. Okay, and then this is what energy use looks like. Now this is what energy use looks like in 2000. In RCP 2.6, notice that coal is way down, natural gas is up. Natural gas is a more carbon efficient fuel. It still emits CO2, but much less CO2 per unit energy. And invariably, some of this coal is subject to something called carbon capture and storage, and so on and so forth. And in 8.5, we still use a lot of coal, oil, and natural gas and a lot of energy in total. And for these ones, we use less. So, I mean, that's basically, if we use less fossil fuels, we get less warming. I find it interesting that the amount of solar, wind, and geothermal is really small in all of these. I'm of the opinion that that could be a larger piece of the pie, but maybe I'm overly idealistic. Bioenergy is a major factor here in RCP 2.6. Nuclear is marginal. I mean, you might call me a hippie for saying we should be doing more in terms of solar wind. I think whether we like it or not, nuclear is probably also a bigger part of the picture than this stuff is here. I'm surprised to see the role of bioenergy there. But we'll see. The point is that we have decisions in terms of what the bar graph looks like, and those decisions matter. Okay, again, returning to the future here to kind of summarize. Okay, we get to choose which one of these paths we follow, and that has to do with what kind of personal decisions we make, and also who we elect, and and what kind of energy we're willing to buy, and what we're willing to express to our energy companies to do that. All scenarios predict warming. I mean, we bought into some amount of global warming, but again, we can choose between RCP 2.6 and RCP 8.5. The other thing here is that climate stability is assumed by default. Okay, we might have climate instability. Just to show you what else, a couple other things these things mean. If we're at RCP 2.6, ocean pH levels off, and if we're at RCP 8.5, we get by about 4 pH units, which is about a 5-fold increase in acidity and hydrogen ion concentration. And in terms of September sea ice extent, at 8.5 we're out of sea ice there's no ice in the Arctic in the summer ever by 2050. It's almost gone in RCP 6.0. If we stay with 2.6, it will reduce, but we'll still have some ice there in the Arctic. So there you go. There you have it. That's the end of the story. We have made it to the end.